So here we are with the last video, yay, for the cardiovascular system, and we're going to be looking now at venous blood flow in the body. So at the venous side of the capillary networks, blood pressure is 16, 18 millimeters mercury, give or take, and by the time the blood reaches the right atrium, blood pressure is reduced to only about 2 millimeters mercury. Now, if you're lying down, that's sufficient blood pressure differential to get the blood back to the heart. But if you're standing up, it works for the brain, but not so much for the inferior vena cava. There's so much gravity, the force of gravity pulling downward on the blood will overcome this 16 millimeters mercury differential between the venous side of the capillary networks and the heart. So how do we get blood back to the heart then? Because clearly if we're standing up, we don't die. So something must be working for us. Well, we've already talked a little bit about the veins and how they have the valves, those one-way valves in the veins. So one of the ways that we push blood through the veins and use the one-way valves to move blood forward is because of muscular compression. So as the muscles squeeze on the veins that are right nearby, they push the blood that's here in this compartment upward. And when the muscles relax, then the blood may fall back down, but when it does, it closes the veins. So blood pressure pushes the valves in the veins closed. And then another squeeze will push more blood upward, pushing it on into the next segment of the system. So we push upward, that blood will then fall down and close it, then more push here, pushes blood upward, pushing all of this blood upward, which pushes all of this blood upward, and you get the point. So these one-way valves help to ensure that the blood is always moving only toward the heart. But we have a second system that comes into play here, and that is our breathing. So if I'm going to draw the trunk, here are the lungs, and here's the diaphragm. So arms going out, but we're going to say that here is the diaphragm. So this is when we are exhaling and the diaphragm is at rest. It is longer then. But as we take a breath inward, the diaphragm flattens out, which then increases the volume of the thoracic cavity and decreases the volume of the abdominopelvic cavity. Now we've got the inferior vena cava flowing through here. So when we decrease the volume of the of the abdominopelvic cavity, that puts pressure on the blood in the lower portion of the vena cava, the inferior vena cava, and pushes the blood upward. Now, also, as we increase the volume here of the thoracic cavity, here are the lungs, that reduces the pressure around the vena cava and actually pulls it open some. So we're pushing here and we're drawing up into the thoracic portion of the inferior vena cava. So the more we breathe and the deeper we breathe, the more we push and pull blood upward toward where the heart is. Of course, the heart is sitting right here. So the good news about this is that exercise or using our muscles and breathing deeply will increase the effect of both the muscular compression, pushing blood back toward the heart using the one-way valves, and the effect of this respiratory pump. And that will really force the heart into maximal function. So blood pressure then is super important for moving blood around. So there's one last thing to talk about here, and that is the idea of what's called central venous pressure. Central venous pressure is a measurement of blood pressure here at the right atrium, where the superior and inferior vena cava are bringing blood back to the heart. So normally central venous pressure is about 2 millimeters mercury. And out here at the capillary networks, remember, we're like 16 or 18 millimeters mercury. So we've got this, let's just say 16, we'll go with that number. We've got about a 14 millimeter mercury differential between the capillary networks and the heart. But if something occurs to cause this central venous pressure to increase, let's say it went up to 6 millimeters mercury, then that's going to reduce the differential here. We're going to take it down from 14 to just 10. That makes it even harder to push blood back up toward the heart. So what's the effect of this? If we're not pushing as much blood back toward the heart, then that's going to cause a buildup of blood pressure here. So maybe this is going to now jump to 20 millimeters mercury, which will then affect the capillary networks, making it harder to pull fluids out of the peripheral tissues and into the blood. And the result is edema out there in the peripheral tissues. So an increase in central venous pressure results in edema back in the peripheral tissues, out in the arms, the legs, around the abdomen, and that is an uncomfortable situation for any person. All right, so that's everything I got to tell you about the cardiovascular system. You know how to reach me if we have any questions. So study well, and I'll see you in class next week. Oh, rats! I'm sorry. We got one last slide. It's about venoconstriction. I apologize. Because the veins have less smooth muscle in their tunica media, the vessels tend to be larger and kind of slack. This creates the opportunity to maintain a reserve of blood. If we let the venous system go slack, then we increase the volume of the venous system. And the blood can be, I'm going to put this stored, it effectively stores blood, but the blood is still flowing along. It's just flowing a little more sluggishly because we're not requiring this blood to move quickly back to the heart. But if blood pressure falls and becomes too low, then the medulla will send a signal out to constrict these veins, making them tighter and smaller, and now that blood is going to be mobilized and brought into the back toward the heart, and that will increase central venous pressure if central venous pressure gets too low.